Ladies and gentlemen, I welcome you back for the second presentation by Dr. M.R.Srinivasan, Member, Atomic Energy Commission since 2005. He has served as one of the India's foremost nuclear energy experts and science administrator. He was Chairman, Atomic Energy Commission, and founder chairman of the Nuclear Power Corporation of the Department of Atomic Energy from 1987 to 1990. He joined the Department of Atomic Energy in 1956 in Homi Bhabha team and played a crucial role in setting up a nuclear power stations. He served as advisor, International Atomic Energy Agency, Vienna, from 1990 to 2002, as member of the Planning Commission from 1996 to 98, as member of the National Security Advisory Board from 2000 to 2005. He is a founder member of the World Association of Nuclear Operators. He has served several important international think tanks and task forces advising the government of the energy and security issues, such as Indo-US engagement in connection with the nuclear deal and nuclear cooperation with several countries around the world. He has served as a prominent delegate of the International Pugwash Conference on Science, Society, and Nuclear Disarmament, and also key international conferences such as the Plutonium Futures. He is the recipient of Padma Shri and Padma Bhushan, the Indian National Academy of Engineering Lifetime Achievement Award, the Homi Bhabha Lifetime Achievement Award from Indian Nuclear Society, Homi Bhabha Gold Medal from Indian Science Congress, Distinguished Alumni Award from the Vishwesvaraya College of Engineering. He has authored the Penguin publication, From Fission to Fusion, the story of the Indian nuclear power program, besides scores of papers published in the national and international journals. The Hindu carried his column on nuclear issues for many years. I have great privilege of welcoming Dr. Srinivasan. Dr. Srinivasan.
Yeah, thank you. Professor Ramurthy, Professor Srikantan, Professor Shetter, many friends of mine who are in the audience, ladies and gentlemen. A few days after the Japanese nuclear disaster occurred, I got a telephone call from Professor Shetter that he wanted me to come and speak here, and he suggested that I should do that as early as I could. So I told him that I was coming to Bangalore in the last week of March, and that we could fix a date then. So we had initially thought of some dates which became difficult to confirm because of other programs and so forth. And so the earliest date that was feasible happened to be today. Well, I think it is very, shall we say, appropriate that the National Institute of Advanced Study today thought it appropriate and timely to have a discussion on this Fukushima situation, and also to find out what lessons we have to learn in moving on. Incidentally, I happen to be one of the few people in the Indian nuclear community who actually has been in Fukushima. This was way back in 1982 when I had gone to Japan for some other work. At the time, we were trying to get some components for our Tarapur stations. And since Japan had moved ahead on making of certain components for the boiling water reactors, they offered to supply some because the Americans had stopped supplying this, any components, spare parts, and such like for our Tarapur reactors after 1974. And I was then very impressed at the large number of reactors that they had built and the way they were building future reactors in a very, shall we say, workmanlike way with short construction time and so forth. At that time, incidentally, the name Daiichi in Japanese means number one, and Daini means number two. And Daiichi is the first of the Fukushima complexes, which has got 6 reactors. The Daini has got 4 reactors in that complex. And after I had been in Fukushima, I also started thinking that it was a good idea for us to build these similarly large nuclear parks. Other parts of the world hadn't actually gone beyond maybe 2 reactors at a given location. The Japanese had already thought in terms of 4, 6, and so on. And later on, it became fairly standard practice to have not just 2, but maybe 4 reactors at a given location. And I happened to advise Rajiv Gandhi that it was probably a good thing for us also to plan on the so-called power parks, nuclear power parks, because of some advantages of sharing of trained manpower, infrastructure, and so forth. But I'll come back to this as we go on. But I'll first discuss the Japanese event in some detail. When the earthquake, incidentally, I must compliment Dr. Rajendran, Dr. Ms. Rajendran, for the very interesting talk she gave on the tsunamis, and in fact it has served as a backdrop to the story that I will be relating. In some ways it takes off from the background that she has given. At the time the earthquake took place, the status of the #1 Fukushima power station was the following. Units 1, 2, and 3, they shut down automatically. This is because we provide seismic sensors. Oh, you want me to use this, is it? Okay. Yeah. The seismic sensors are provided, and they shut down these installations when earth motions beyond a certain level take place. And so the 3 operating units shut down. It so turned out units 4, 5, and 6 were under maintenance and refueling outage, so they continued to be in a safe condition. In the #2 Fukushima, also due to the earthquake sensors, the 4 operating units shut down automatically. These 10 units belong to Tokyo Electric Power Company called TEPCO. It's a leading electric utility in Japan, even in global terms, with strong engineering tradition, good profitability, and good professionalism, and so forth. So it's a good company. Then in another installation, slightly northeast of Fukushima, is this power station called Onagawa. There also the 3 units shut down automatically. Now, when the reactor shuts down automatically, the nuclear chain reaction is terminated. There is no more new fission of uranium or plutonium is taking place, and therefore a large part of the energy release, which comes out as heat, stops. But you have to remember something that's rather unique. Of course, Dr. Rajendran mentioned the very genesis of the heat of the Earth, which is the decay of radioactive substances. She mentioned in the context of the heat that is there. You know, for instance, somewhere if you go maybe 100 kilometers below the Earth's surface, you got a hot core. And in fact, some people think at some point of time in the future, we may be able to harvest the heat from that hot core as a source of energy. Of course, the big challenges are there to go that deep, extract that heat, and so forth. But that heat is also coming out as a result of the fact there's a lot of radioactive material in the core of the Earth, and that is giving out radiations which manifest as heat. So in the case of a nuclear reactor, even after the fission reaction stops by insertion of control rods which absorb neutrons, the fuel continues to be radioactive, and this heat production is generally called decay heat. Some people call it gamma heating, decay heat, or whatever. It is the radioactive substances which keep on giving out the heat. And if you don't take out that heat, then the heat builds up and it can reach dangerous proportions. So cooling of a reactor, even in the shutdown condition, is extremely important. So in the design of these reactors, we provide many redundant systems, backup for backup, to make sure that we can keep the heart of the reactor, we call it the core, which contains the uranium fuel, cool at all times, cool enough so that there is no danger to the plant, and there is no danger to the environment, and no danger to people by way of escape of radioactive substances. Well, we have already seen the geographic location. Well, I think it's adequate to just concentrate here. Fukushima is some little distance north of Tokyo, and the two stations are shown in some detail. The Daiichi complex is shown there. That's where the problem arose. This is what you see here is the 4 units of the Daini, and the Daiichi complex is in that direction. There's only a short distance that separates these 10 reactors. The Daiichi plant, which has been in trouble, has reactors of this kind. The first one, well, incidentally, these are all called boiling water reactors. We have 2 of them in Tarapur. They predate these reactors. In fact, we can say ours are some of the early reactors, the boiling water kind. And these are reactors based on similar principles developed by General Electric Company of the United States, but scaled up in size. Number 1, 460 megawatts. Our Tarapur reactors, when they were originally rated, was about half the size. But then subsequently, because we did some modification and removed some equipment, we are operating at a lower output. And so it's closer to, it's about 160 megawatts we are operating. Now, our Tarapur reactors went into operation in 1969, and this went into operation in 71. So, in fact, Tarapur is earlier than these. In between, General Electric Company built another boiling water reactor of not such a large size in a place called Suruga, slightly after our Tarapur reactors were built. The subsequent reactors 2, 3, and 4, 5 are larger in size, 780 megawatts, and some are built by GE along with Toshiba, a Japanese partner, more work by Toshiba, some by another Japanese partner, Hitachi, and then the number 6 reactor is a larger one, 1,100 megawatts, went into operation in 1979. Of course, you must remember that the early reactors, they belong to design vintage of 1960s, rather like our Tarapur reactors. We started work on Tarapur reactors in 1964, and we completed them in 1969. So they are all early generation reactors. See, this is what the power plant looked before the earthquake and tsunami, and this is what the plant looked after. Of course, you must notice that although the severity of the earthquake was very, very high, actually the reactors withstood the high seismic disturbances, but certain things happened in the subsequent tsunami of some very high magnitude. The tsunami, as was mentioned, reached extremely high levels. In other words, flooding of the area took place. And you can imagine what would have happened at the time when the earthquake and tsunami struck. There was a crew which was operating the power station who were there inside the plant. And the entire area, some 10, 15, 20 kilometers, had been flooded out. Probably other operators who were living in this general neighborhood would not have been able to get out of their homes. Homes may have been destroyed. Their families may have been wiped out. So it was very difficult for even the plant operators to get there. And only the people who were there at the plant continued to do something to keep things going. In fact, 2 people went down to the basement to start some diesel sets. They thought they could do something. And by the time they got there, the onrush of the tsunami was such that they were drowned instantaneously. And in fact, it was many days later when they could gain access, they found the bodies of these two people. Of course, the workers continued to do whatever they could, but the odds were really stacked against them. The sequence of events, well, a point that was mentioned by Dr. Rajendran, it is not a deep earthquake. It's very important. A shallow earthquake brings in much more serious tsunami. You can understand that. If it is deep within, some amount of the forces get dissipated in disturbing the earth. But here, all of that force was available for pushing the water, and therefore the tsunami intensity was extremely high. First thing that happened was, of course, the unit shut down, as I mentioned earlier, and immediately the Japanese government declared a nuclear emergency, and they said people within 3 kilometers must move out, and they also said that people living in the 3 to 10 kilometer radius should take shelter, not expose themselves to possible cloud, radioactive cloud that may come from the power station. Now, in keeping in trying to appreciate the size of this tragedy, you must bear in mind that there were two other serious accidents that took place before this in the nuclear business. One was the 3 Mile Island accident in the United States in 1979. At that time, also similar problems of loss of cooling for the uranium and hydrogen buildup, possible explosion, all that took place, evacuation of people took place, and so on. But they had to deal only with one reactor emergency. Of course, it was a larger reactor, 1,000 megawatts or 900 megawatts roughly, but they had to deal with one reactor. In the case of Chernobyl, which took place in 1986, April, 25 years, in fact, this April 26, what happened is the top of the reactor blew off, and although the reactor was shut down fairly soon thereafter, because it was a reactor that was using graphite as one of the structural members, a large amount of graphite, which is exposed to air, graphite started burning, so the uranium also started burning and spreading, etc. And they had to do a heroic task of dumping large amounts of sand with boron, concrete with boron from helicopters to try and cover up that one. But they had 4 reactors there, but the problem was with one reactor. Here in Fukushima, the same type of event knocked out 3 reactors and brought 3 of them into emergency condition. How that happened is the following. First of all, the cooling that was required for the fuel in the shutdown condition was not available. Normally, of course, there is a turbine system which provides cooling. Then there is a so-called emergency core cooling, which is supposed to remove, or rather it's called the shutdown core cooling, which is to remove the heat of the core from the shutdown condition. That was not available because of the fact that the Fukushima power station got disconnected from the grid system. External power supply, which normally comes from different places, didn't come. They got knocked out because tsunami knocked out transmission towers, lines, and so forth. Now, in the Indian condition, which I'll come to later, we take a lot of precautions because it's not an unusual occurrence in India for grids to fail. It happens all the time, so that we make multiple arrangements, and to some extent, because of our rather less well-tuned conditions, we are prepared for that. Here, we were told that over the last 20 years, there has been no case at all when the power station had got disconnected from outside power. In other words, it is rather like an American or a European doctor trying to treat malaria. If a person inflicted malaria were to go to US or Europe, he's likely to die because they haven't seen malaria. Whereas, of course, in India, even a common garden doctor will probably tell you it's malaria and somehow see that you are not knocked out. So that's the kind of situation that happened here. What happened first is that as a result of loss of cooling, the so-called containment pressure, I'll show some sketches which will make you understand what this containment is. It reached double the design value. So already a kind of a dangerous condition. Then a little later, this isotope is called cesium-137, is a product of the breakdown of uranium, which meant that some fuel had got exposed, and that fission product, as we call it, had come out into the environment. Of course, radiation level at the site boundary showed an immediate spike, but it, of course, went beyond the regulatory limit, but then it came down a little later. But March 12th, the roof of unit number 1, it blew off. This is a concrete building around the reactor containment building. Again, I'll show you a picture later. The reactor itself is a heavy steel wall building. Not building, it's a steel wall vessel. The steel thickness being of the order of 8 to 10 inches, or 8, 9 inches anyway. And that is designed for high pressure. And it is within that the uranium core is kept and the cooling water goes there. Now that is encased in another steel containment vessel in the earlier designs. Later on, it's steel backed by concrete, and that particular enclosure is called a Drywell. And beyond that, there is a concrete industrial kind of structure, concrete and steel. Now, it is the roof of that building that blew off. It blew off, it was established to be due to hydrogen explosion. How hydrogen comes out is when the material we use for covering the uranium to see that the dangerous substances within the uranium don't get out into the cooling water is a material called zirconium. It's a very special material. And that zirconium, if it is hot and comes into contact with water or steam, it breaks the chemical bond between hydrogen and oxygen, and hydrogen is released. And if the hydrogen then comes in contact with air in a certain mixture, it becomes explosive, and that kind of explosion took place there. Immediately thereafter, the Prime Minister ordered evacuation of people in the 20-kilometer zone. And in this period, the owners of the plant, Tokyo Electric Power, would have tried to desperately bring in some way of cooling the cores, because they would have realized that the provisions made in the plant design somehow are no more available, because they could not construct how exactly all those systems got dislocated or disturbed. They then thought in a desperate way that the only option left to them was to inject seawater. Seawater, of course, available in great abundance. But of course, in taking the decision, they would have realized quite clearly that that decision meant that the possibility of restart of these reactors was pretty low, because these reactors are made with substances such as high-quality stainless steel, zirconium, and so on. And if you were to start putting seawater with a lot of sodium chloride in it, it will corrode many parts of the reactor, and reviving the reactor after such an exposure would become very difficult. So it's entirely possible that they were troubled whether this option was something that they should consider, but they seem to have had no alternative, and so they decided to start thinking of putting in seawater. But this was not easy, because there was a lot of debris, physical debris around these disabled reactors. The pipelines had all got disrupted, and the electrical connections were all knocked out. And so one option was to consider dumping seawater from helicopters. So they tried doing that. And you would have seen pictures in the TV screen that they tried to dump in seawater from helicopters. And in the meantime, they brought in high-capacity firefighting pumps from elsewhere with heavy hoses, and they tried to pump in seawater onto these disabled reactors. Now, they started the seawater injection in number 1 unit, 12th March, 13th March, number 3 unit. And then on 14th March, there was a hydrogen explosion in unit number 3, much the same kind of reasons. That is to say, fuel has been exposed, hydrogen has been formed, pressure has got built up, it has got into the building, and there in contact with the air, hydrogen is blown up. Now, in addition, of course, they got confirmatory evidence that the water levels in reactor number 3 started going down drastically. Then complete evacuation in 20 kilometer radius. Then at that point of time, they also started to distribute what's called a stable iodine. I must tell you what this means. You see, one of the substances that come out when spent fuel after being in the reactor is exposed to air, one of the isotopes that comes out is what's called as radioiodine. It's a radioactive equivalent of normal iodine. And the body has a natural tendency to take up iodine and store it in the thyroid. Incidentally, if you don't have proper amount of iodine, your thyroid function suffers. So iodine is required for the body's health. But if you were to pick up radioiodine and it lodges in your thyroid, then the radiation from the radioiodine can actually create a cancer. And therefore, what is done is, risk is especially high for children. So what is done is to block the natural tendency of a human body to pick up iodine, which could be the radioactive type of iodine, by seeing to it that you saturate your own body thyroid with a lot of stable iodine. So this is one precautionary measure. And so around nuclear installations, to deal with this kind of emergency, we keep available potassium iodide in the form of tablets or salt or whatever, and we administer that to especially children and even to other people. So they started doing that as a precautionary measure. And then on 15th, number 2 unit had another kind of problem, another component of the reactor called the suppression pool. There was an explosion and that got damaged. In the meantime, unit number 4, which was not actually in operation, had another kind of problem. What had happened in unit number 4 was they had taken out all the fuel from within the core and kept it in what's called as a spent fuel pool, which is there adjacent in the top of the reactor building, in order to carry out some maintenance activities and also do refueling. Now, that spent fuel also, because it's been in the reactor for some time, needs cooling. As a result of physical damage that would have taken place as a result of explosions in the neighboring structures and so forth, the water in the spent fuel pool of this unit number 4 seems to have got drained off, and that exposed that fuel, and therefore fire started. The zirconium, hydrogen, all of that started a fire, and then they tried to put it out by pouring in seawater from the helicopter and so forth. Of course, they managed to extinguish the fire, but now on March 15, they said people in the 20 to 30 kilometer radius, they were also asked to stay indoors, not to expose themselves to the air, general air, because of some fear of contaminated substances in the air. And they also advised people not to eat vegetables produced in the neighboring area, because the fallout, the radioactive fallout generally comes to leafy vegetables like spinach and lettuce or cabbage and so forth, and also milk produced there, because cows ingest the leafy substances, and there's a tendency for the radioactive substances to concentrate in the milk. So they said, don't do all that. Now, thereafter, of course, the serious attempts to pour water and bring things under control. Now, I'll show you typically what exactly this boiling water reactor looks like. This is the pressure vessel made of very thick steel. This is another vessel also made of steel, but generally speaking, in the thickness being maybe 1.5 to 3 inches. This is called a Drywell. Normally, now this is also a steel containment building called primary containment. Now, the control rods are these elements that are moved into the core of the reactor. This is the core. The red is the fuel element, and the blue is the water. And the water becomes steam as a result of nuclear heating, and then it goes in through these lines to the turbine. And the rest of it is like a thermal power station where the high pressure hot steam drives the turbine, and then electricity is generated. Then the steam comes into a condenser where it's cooled by seawater or cooling towers, and then the condensate goes back into the reactor. Now, in addition, in this design, there is another a toroidal vessel made of steel, or it could be concrete lined with steel, which is filled with water. The purpose of this vessel and the water is, in case the pressure builds up in this Drywell, the air and steam mixture, they then are forced to go through the water. So the steam condenses, energy transfer takes place, and the pressure comes down, and the balanced air communicates with the rest of the building, and it is in a relatively low pressure, and it doesn't go into the environment. Now, in the case of Tarapur also, we have a similar, this is called a pressure suppression pool, but of a slightly different configuration and larger dimension. We have it. I'll show that to you a little later. Now, in other types of reactors, just briefly, what's called as a pressurized water reactor, like the ones that we are about to start in Kudankulam, the steam doesn't get produced in the reactor vessel. Rather, the hot water from the reactor goes into another set of equipment called steam generators, and there ordinary water, which is not in contact with nuclear fuel, is made into steam, and they drive the turbines, and the reactor water goes around in constant circulation. Of course, later on, in the case of our own reactors, we call heavy water reactors. There's a different configuration altogether, and there also we have indirect production of steam. Reactor water doesn't become steam and go into the turbines, but it is the turbine circuit water, which is normal clean water, that is made into steam. This is another view. They call it so-called Mark I containment. Our Tarapur reactors are pre-Mark I. After our early reactors of Tarapur design, the designer of this plant, General Electric Company, optimized the designs in various ways, and they arrived at Mark I and subsequent designs. Now here, the important thing to take a look at is the spent fuel pool. What happens, even in our Tarapur case, we have this feature, similar feature. When the reactor is, these reactors, either pressurized water or boiling water reactors, they operate for about 12 to 18 months at a time, and they are not fueled on load. That is, we do what we call as off-load refueling. The reactors are shut down once a year or once in 1.5 years, and then a certain amount of new fuel is put in and a certain amount of old fuel is taken out. For doing that, at the top here, we have a spent fuel pool, and all of this thing is submerged in water, and the fuel is taken out of the reactor, taken there. The new fuel is brought into that pool and put into the reactor. Well, here, I think we show the status of the different. I told you earlier that we need to keep the fuel pools cool, and the condition that pools was the following. Unit 3 and 4, water level was low. Unit 3, fuel rods got damaged. 5 and 6, which actually were not knocked out by tsunami or the earthquake, they also started to lose some water. Chances are that certain other types of defects might have shown up over a period of time due to physical damage in the surrounding area. But of course, they were brought under control very quickly because there had not been any serious problem, but some, shall we say, checks and equipment, valves and so forth, retrieved the situation. But in the case of Unit 4, this is where the fuel got exposed. Now, amount of fuel has molten, and that is what is being given out to the radioactive substances. The seawater is being pushed into all these reactors. Now, in one particular case, number 2 unit, this suppression pool had an explosion there. And the roof, this is the concrete and steel building, industrial type of building. This has been blown out in 2 reactors, 1 and 3. Well, I think this is going to too many details, because I think if I am to cover all the technical details, I'm going to take too much time. How much time do I have, Professor? Oh, I think I can skip some of the, well, anyway, what happened in one particular case, number 2 unit, this structure has failed largely because unless we keep on cooling this water here, you are not able to make sure that the pressure inside this containment can be brought down, because there is energy being put in, and if it's not being taken out in some way, then soon enough this water will boil over, evaporate, and then it's unable to bring the pressure down. So that's what happened, and therefore there's an explosion here. And the published reports that radioactive water is going into the sea is from number 2 reactor, and somewhere here the floor has opened up, and they have said there is a gap of something like 8 feet, and they're trying to pour in concrete to prevent escape of radioactive water to the sea. Well, I think here just very briefly put a normal operation, water is up to that level. Beyond that is a steam space. So this is a safe condition. And then there is water here, and any high pressure built up, the steam is condensed here, and the pressures are all kept low. Then, in the event there is less water, see here, you see from the previous one, water level has come down, and the pressure builds up, then automatically there are pressure relief valves provided in the circuit, and they relieve the pressure inside this vessel, because we do not want at any cost this reactor vessel to be jeopardized. So the pressure is relieved, but in the process, the pressure in this part builds up. And that has to be controlled by cooling here. And if the cooling here is not there, then you are unable to reduce the pressure. Yeah, that's what happened here, you see. Here, the water got lost, and the pressure got, the pressurization of all of these parts took place. And this goes to show how the steam water mixture is building up, and then you will see it is trying to get out, it breaches the gaskets at the top and get out into the reactor building. Next one, escaping into this area, hydrogen goes there, and then explosion takes place. That's what happened. And then this building, the concrete walls, they opened up and they burst out. The building looked like this, and after the explosion, that's what it looks like. Well, I think there are similar kinds of pictures, excepting that in the case of number 2, there was after some time, there was an explosion here, and more trouble. Now, these are the radiation levels. Well, the numbers, I think, are too, shall we say, they're for a profession of interest. I'll skip and to tell you that radiation can be detected at extremely low levels. The instrumentation techniques have gone so advanced, it's possible to detect extremely low levels of radiation. We can identify the particular isotope which is putting out that particular type of radiation. But it doesn't mean that all this radiation is dangerous necessarily. But certainly there's public panic, because if the situation goes out of control, there's no credibility that people are able to bring this under control. Then, of course, there will be widespread risk of exposure of many people to levels that are not considered safe. So that's the kind of situation we are having. And these are all different points of time, monitoring locations and all that, the information is available. And, you know, this is just to tell you, this micro-sievert is a unit of radiation measurement. In the old days, we used to use another term called millirem. There is 1,500 microsievert is 150 millirem, if you divide by 10. But anyway, all these measurements certainly are causing the kind of concern on people, what's going to happen to our health and so forth. But just to give you an idea of the permitted levels internationally accepted and what we are adopting in India, I'll just spend a minute here. Under normal operation, the International Committee on Radiological Protection, now this is a body that's been in existence even prior to the nuclear power business. This ICRP, as we call it, it was founded in the early 50s when people were only using radiation for X-ray purposes and so on. And even based on the information then available, they set certain limits, and over a period of time this has been revised, and revised, generally speaking, downward. What is considered safe for the public is 1,000 microsieverts, and our Atomic Energy Regulatory Board also prescribes the same limit, 1,000 microsieverts per year. For occupational workers, it can be 50,000 microsieverts, or call it 5 rem, we call it, as per the International Commission's recommendation, but we actually brought it down to 3 rems. The nuclear power plants around the world, they're always trying to see that there's still a margin below what is permitted by the International Commission as a matter of caution and prudence. Now, under accident conditions, the International Commission permits twice this value in one exposure. That is to say, you can have 100,000 microsieverts or 10 rem. Now, it's rather revealing to take a look at what is the situation in nature. For instance, Finland, interestingly, has a very high average annual dose because it's got underlain by a lot of granite. And granitic rocks contain uranium in some amounts. And then you will find, of course, India comes somewhere, I think here we are. Our average background dose in India is 2,400 microsieverts per year. But in Kerala, this can be about 4 times as much in the beach sands of Kerala. And some countries are low, some countries are high. So there's a bit of a variation even in the natural doses. So all I'm trying to say is that radiation is a part of the environment of the very earth we are made of, because radioactive substances are there. In some places more, in some places less. Incidentally, those of us who keep traveling a great deal by international or even aircraft within the country, etc., flying high, we are always exposed to a fairly high amount of radiation because of cosmic rays which come from the outer sources, and the kind of shielding that the atmosphere is providing is absent. So if you keep on traveling frequently by jet aircraft flying high, we pick up a fair amount of radiation. Now, of course, this is a subject of its own, but I'll just like to very briefly convey what are the kinds of effects that you get. No detectable effect less than 25 rems. Nausea, vomiting, reduced immunity to other infections, 100 to 300 rems. Fatality, 50% of the cases if it exceeds 450 rems. And within 30 days if it exceeds 600 rems. Chronic exposure, there will be slight increases in susceptibility to cancer, especially to leukemia, and to cataracts and so forth, but then they're pretty high levels. These levels are not, in fact, being experienced. The people who are really exposed to high levels are the people who are working in the plant in trying to bring the situation under control. People who have been evacuated now beyond 20 kilometers, they really do not have a very high risk of exposure. But what's happened now is they're asking people there not to drink the local water. In fact, the two initial relief substances that were sent from India, one was one whole aircraft full of blankets, and the second was another aircraft full of drinking bottled water from India. These were sent as relief because they were very worried, especially for the children, that they should not drink any of the local water, again as a result of seeing to it that they do not pick up radioiodine or other radioactive substances. Now, I'll quickly go through the Indian reactors in this context. The first two reactors, Tarapur, they have been in operation now for 40 years. 1969, they were put into operation. 2009, 40 years was completed, so we now completed 41 years. In our case, the suppression pools are like this, rectangular. They're very large in volume. It's an early design, fortunately. The result of that is very low possibility of pressure buildup because we have enormous amount of space there, and we've got also very large amounts of water inventory which enable various types of conditions, off-normal conditions, to be contended with without any serious risk. In addition, we have, from the original design itself, what we have called an emergency condenser, which is so located at great height that it is possible to cool the reactor water through natural circulation. You know, the principle is, it's rather like a chimney. When you've got air which gets heated up, through its own buoyancy forces, the air rises because the hot air is lighter than the cold air, and therefore the hot air rises, and the cold air is then sucked in from whichever place the cold air is available. So this is called thermosiphon. And this arrangement is such that once we cool that condenser, this water doesn't require any pumping at all. It just goes up and down on its own. The driving force is the density difference. So we have this condenser, and that is in turn cooled from water from outside. And therefore, this is an additional feature that we have that were not there in the Japanese systems. Another very important thing is the blackout, as we call it. That is when the station gets disconnected from the grid system. We have had a number of examples where such a thing has happened, but we have found that the various safety requirements have been met as a result of diversity, number of parallel systems, alternative systems, and so forth. So we have got, of course, the reactor, what we call shutdown scram systems. Now, they take place under different circumstances, but we ensure the cooling of the reactor through different mechanisms. The emergency condenser, which I mentioned to you earlier, is valved in, and that is powered with battery sources, so we don't require an external source. We also have a manual operation that's available from an accessible area, and so on. So we have done a recheck when the reactor was relicensed for continuing operation. So we have provided some additional diesel generator sets at higher levels and all that. All that has been done in the last few years. And one more recheck is going on to make sure or to reconfirm whether any further backfitting is required. Incidentally, I must mention that in the Tarapur case, there has been no technical contact with the original reactor designer, General Electric Company, or any US organization after 1978, when the US passed this Non-Proliferation Act, because they said that they had to suspend all relationship with India. So we've been doing our own analysis, backfitting, additional equipment, and so forth. So I think we've been doing a thorough job, in a sense, almost like designers of the plant, unlike depending on another designer's advice and so forth. So there's a great deal of in-house competence that got built up. Now, so our analysis show that the available provisions of the original design as augmented by various additional features that are put in, we are able to maintain the reactors under subcritical and cooled condition due to various provisions that have been incorporated there, either originally or backfitted later on. Oh, I think I must go there. Oh, no, next one. Yeah. Now, very briefly, the reactors that we are having in other places, these are all called heavy water reactors, and these are all engineered on our own, and many of our reactors are all heavy water reactors. Of the 20 that we are now operating, 18 of them are heavy water reactors, and they have a different configuration. Here the reactor vessel is horizontal, the fuel is placed in what are called as coolant channels, and these are the mechanisms to control the reactivity. The hot heavy water goes to the steam generators, and the water from the turbine circuit comes to the steam generator, and that becomes steam, goes to the steam turbine. Now here also the configuration is such that we are able to maintain a certain degree of thermocycling, that is natural convection cooling. And then our design, in all our cases, we are providing what we call as double containment. The inner reactor building is made out of pre-stressed concrete to withstand high pressure. There is a second building which can actually withstand an aircraft impact also. And the space in between is kept at a negative pressure so that any leakage goes into the space, and that air is put through filters to remove any radioactive substances and then let out. So we have a different kind of concept, and again, we have checked out, even in the background of what has happened in Fukushima, how secure our safety systems are. Of course, studies are going on, but the initial indications are that they seem to be quite robust. Well, of course, if all power supplies are lost, then it's important to ensure that heat removal takes place in some reasonable time before the fuel starts heating up. Of course, in our case, we have done some inventory analysis of what's the amount of time, for example, the entire reactor to boil out, how many hours it will take place, and so on. So these are all to make sure that we have adequate water inventory. For example, just to give you in a very nutshell, in Kalpakam, very close to our two operating reactors, we have built a lake. We get water from the Palar River, and we've got a lake which has got many days equivalent of water very close to us. Very important to have the water inventory close to you. Otherwise, you'll get into difficulty. Well, this shows pictorially how typically the fuel is encapsulated. First, that is the uranium. It's got the zirconium alloy shield, and then there is the primary coolant is out around it, which is in the case of our heavy water reactors, heavy water. And then there is a containment, and then there is an exclusion boundary. And so now, very briefly to Kudankulam. Now, these are the two reactors that are now in an advanced stage of construction. In fact, fuel loading we should be ready for fuel loading next month. And I'll briefly explain. This is a much larger reactor. This is going to be our first large reactor, 1,000 megawatts, which Russia is cooperating with us to build. In this case, this is a pressurized water reactor type, not the boiling water reactor. This is a pressure vessel, and it's connected to the steam generator. The hot water from the reactor goes into the steam generator, and then the steam from here goes off to the Drywell turbine. Now, with regard to the safety features here this particular inner building is the pre-stressed concrete building, which is also lined with steel and can withstand high internal pressure. And Then there is a second building, also made of concrete, and that can withstand aircraft impact also. This is a present requirement because after the American experience 9/11, the perception of safety has changed. Everybody demands that we should be able to demonstrate safety even in a big jetliner or to come in. Now we have emergency core cooling is provided by special tanks. Then you've got what we call the trace sprinkler systems, which can bring down the pressure inside if there is any steam formation. Then we've got hydrogen control system. There are many hydrogen catalytic recombiners in case hydrogen builds up automatically without going to combustion process. The hydrogen is recombined and made into water, so there's no risk of explosion. Then we have another very interesting feature here, and that is we have located on the outside of this outer containment a whole lot of radiators, rather like motor car radiators, where the secondary side water can be cooled by air. These are all fin tube heat exchangers. You know, a tube has got a lot of fin surface, and that, again, just by exposure to air, it's able to transfer the heat. And this is another cooling device. It's shown as a separate chimney, but actually it's located here on the outer shell. Then we have provided yet another feature here. It's called a core catcher. As a last resort, if this uranium core were to melt, there is a facility for ensuring that it's cooled adequately and doesn't become another dangerous situation to handle. As in fact, people have been fearing in the case of Japan, if they were not able to cool, what would happen. So now, of course, all of these have been designed, factored. This reactor design is called Generation 3 Plus, and these are actually even safer than the ones that Russia has built for itself or even for China. We have added a number of additional features in the original design because we said that we want those features in our context. And now we'll conduct a review having regard to lessons to be learned from Fukushima to make sure that we are taking no chances with regard to the safety of this plant. Now, earthquake, of course, already things have been mentioned briefly. The only point I'd like to mention is that apart from Narora, which is in zone 4, all our other reactors are in zone 3 or zone 2. In fact, Kudankulam is a very stable zone. The others are zone 3. But we do a thorough examination of the structural design, of the equipment design, instrumentation, valves, and all that kind of stuff, both theoretical analysis and shake table tests and so forth, to qualify that they withstand the kind of ground acceleration. Because you would have noticed that these numbers are a good bit smaller than what you have seen in some of the charts that Dr. Rajendran presented, because they were, of course, she was talking of 2G plus and 1.5G and so on. Of course, these are not very, very high forces that have happened there in Japan. In our situation, we don't expect anything like that to happen because of different geological conditions that we have. This goes into some detail about the margins that we have provided for the peak ground acceleration. Now, this is a chart, something similar to what was shown earlier. This is the Makran fault and the 1945 tsunami. Of course, as was mentioned, in the Gulf of Cambay, because of geometry considerations, the waves are quite high, but even in Bombay, it was not all that high. And Tarapur is located there, and the general ground level there, you see, there is a bit of a promontory, and there is a fair amount of difference between the mean sea level and the general grade level there as a result of the levels available to us. Now, Kalpakam, we already heard one of the very severe cyclonic, the tsunami took place, and what happened there at the time was the following. The reactors were shut down because we had notice, as was mentioned, but the seawater did enter the pump house, but that is a pump house that circulates the water to the condensers. But we had the other pumps that were available for the core cooling which had been supplied by electricity from other sources available. They were at much, much higher level than the tsunami levels. We also had diesel generators at also high levels, but it was not necessary to use the diesel generators. It was possible to cool the reactor with the other built-in equipment, and therefore we managed the situation. And within 3 days, because the tsunami retreats very quickly, all of that pump house was cleaned out, and the checks were made, and the plants were restarted, no problem. We also had a large excavation for the fast breeder reactor, very large, deep excavation. Now that got filled up with seawater, and that was actually more of a, shall we say, construction problem we had to deal with, because for some number of days, the top part of the concrete had got contaminated with seawater, which means the bars could get corroded. So we had to remove a certain thickness of the earlier placed concrete, cut off the bars, put new bars in, and put new concrete and rebuild. Now, in addition, Mrs. Rajendran mentioned that the word tsunami actually was not in our consciousness for quite some time. She's quite right, because I remember when, I was involved very much in the design of the Kalpakkam power station, its levels and all that. At that time, we were really concerned about the high cyclonic storms, tidal waves and such like, and the kind of levels we should provide. And on that basis, we made the designs. It was only post-1980 that the tsunami consciousness came. In fact, actually it came from Japan. No, the word tsunami really means in Japanese harbor waves. That's all it means. And when we were doing the initial site selection of Kudankulam, already we had kept in mind the tsunami requirements must be factored in. And the design has been done there. And we have rechecked even after the information from the Indonesian bad tsunami of 2004, and it's checked out, the levels are all adequate. And the new site at Jaitapur, on which a lot of TV debates are taking place, incidentally, I selected that site, as indeed all the other sites too. There, we have a very fortunate situation. The general grade level of this site can in fact be even 20 meters, because it's a very high promontory, and there's no cultivation, no nothing. And we had decided that we would keep 10 meters as the level for the grade with respect to mean sea level. But now we can review this matter, taking into account all this new information that comes. And of course, some question regarding once in 1,000-year prediction, etc., how that affects. So it's not impossible for us to provide for extra seaboard to ensure that some higher margin is provided. We are fortunate that we are not too close to very high intensity earthquakes. That was a point that was made already. But it is necessary for us to collect all the new information that's coming out from Japan and elsewhere, and see to it that we benefit from that to making the designs safer if there is any area that requires to be further beefed up. Well, I think this has all been gone over. I don't think I should. I think these are some descriptive issues to talk about comparison of thermal, nuclear, and all that from risk point of view and so on. But I think that is, it goes into areas like global warming, carbon dioxide, water optimum, energy mix, and so forth. I think that's perhaps a subject on its own. What I'd like to say is the following, that the entire nuclear community in the world is certainly very exercised about what has happened in Japan. And we all realize the Japanese are not novices in technology. They are a country with a very high knowledge base on earthquakes, tsunami, engineering, and so forth. And that they should have had this misfortune is, of course, a great puzzle. But we have to bear in mind that the reactors that have suffered most damage are early generation reactors. Possibly some of those designs, once we do the analysis, may turn out to have been more marginal than acceptable in today's condition. Probably they should have been backfitted over a period of time when the safety was re-evaluated. Certain additional provisions should have been made. Maybe they were not made. Or it's entirely possible that the combination of the high-level earthquake and the very high-level tsunami was something that they actually couldn't have visualized even. It's possible. But these are all issues that require to be looked at, and much of this will be done. I mean, information will come. The international community will, of course, mull over it, and all the national safety bodies will take note of it, no doubt about that. But the first reaction can be, oh no, nuclear power is too dangerous, let us stop it. It can be a legitimate reaction. The other is, well, look, let's just wait, take a look at all the information, and see how we can make our reactor safer. Is that viable economically or not, or is the price too high? All these are issues that we must be looking at and look at these issues objectively. But I'd like to give only one example here of how technology works. Many of you probably are aware that when jet engines were first put into civilian aircraft, the first aircraft was the Comet, which was designed by the British. And they were the first aircrafts which used jet engines. And it was considered to be a great improvement because travel speeds were increased a great deal. But then, after a certain number of them were put into operation, there were about 5 or 6 aircraft crashes. One of them, of course, happened near Calcutta, and many in other parts of the world, too. It was possible at that time to take a view, let's just now stop this thing, it's unnecessary, we don't need this technological advance. But of course, people didn't do that. They went back to the drawing board and asked themselves the question, what went wrong? Eventually, they found there's a phenomenon called metal fatigue. Like human beings fatiguing, if you have metal also, which is subjected to tension, I'm talking physical tension, not mental tension, that over a period of time, the metal also may behave differently from what it was when it was young. So that can be called metal fatigue. And then they found, okay, yes, we understand this thing and we can design it better. And now people accept jet air travel as something acceptable, not really to be ruled out. Still, new information comes. Last few days ago, we had one case where a Boeing 737, the top part of the roof, the huge hole was created, some piece of metal flew away. So there is still some area of new learning. Maybe it could have been an electric storm, magnetic storm, or some corrosion that has taken place due to some other substances in the air, or whatever. So once again, we've got to keep relearning. So when you deal with technology, there is no settled issue. And of course, one option is, of course, if we were all living some 2,000 years ago, small populations, we could just live quite simply, harvest nature, and be nice, happy communities. But now, 6 billion, going on to 9 billion, people's expectations, requirement of energy, requirement of energy for industries, for agriculture, for homes, for businesses. You have to provide it in some way. You either put out a lot of carbon, you've got a carbon problem, or you try and put a lot of thermal solar power stations, 20 rupees a kilowatt hour or more. So these are all very complex issues. And a country with 1 billion plus, without any intention to stabilize our population, still growing, we have to have the additional source of energy. But of course, it's a constant challenge. How much risk, how much benefit? So I leave the subject there. Thank you.
Thank you very much. And I think the exposition was so lucid and so illustrative that it may not have any questions in you, but still, 1 or 2 questions could be. We are already, it is dinner time, but there is scope for 1 or 2 questions. Yeah, please.
What is the lifetime of a plant? The lifetime of a nuclear power plant or any power plant?
Yeah. You know, when these nuclear power plants were built, the design objective was that we should build them safe enough for 40 years. But many of the utilities, they took a more cautious view. They said, no, we will amortize them in 25 years. That you get the investment back in 25 years. And we have found that by reviewing the safety levels periodically that we can operate them for longer periods of time. And the utilities have derived the benefit. In other words, the investment has been recovered, and subsequently you only pay the running costs, and therefore you are able to make good profits, which you can plow back into further generation projects. Now, this is exactly what happened in Tarapur. We had initially assigned an economic life of 25 years. Now we have completed 40 years. Today, Tarapur is selling power and making profit at less than 1 rupee per kilowatt hour. So you can understand that is very competitive, less than 1 rupee per kilowatt hour. Now, the new generation of reactors, they have assigned a higher life, 60 years. That is based on the life of the so-called irreplaceable components. The irreplaceable components are the concrete structure, the major equipment like the reactor pressure vessel, the steam generator, primary pump bowls, and so on. But you can always replace motor windings, transformer windings, sensors, update the instrumentation and all that. So now the general thinking is that it is possible to design these reactors for 60-year life. That is the general thinking.
Can you please explain now there is a huge cry that solar energy as compared to nuclear energy is not properly exploited in India. Now can you please give some comparison of cost and analysis and in terms of percentage of solar energy exploited in our country with respect to the other developed countries?
Yeah, I think this is a good question. Problem now is solar energy, you're quite right, we haven't developed it adequately in India. In fact, even in the rest of the world also, not a great deal of solar energy. The people who are doing a bit more than others, Germany is one country where they are now giving active support for solar energy, even on private homes, to putting solar panels, and then giving them the benefit of the highest cost of power. The way it works is, you know, power cost in a free market situation depends on supply and demand. When the demand is highest, the charges should be highest. That is in the, let's say, evening peak period when everybody turn on television sets, domestic appliances and so forth, or in the midday peak when all the industries are running flat out. At that peak, you can charge consumer more. But when nobody is wanting the energy, which is in the middle of the night, you should be charging less. Of course, these are fine principles that operate in some societies, not in India. This time of day metering and all that doesn't actually happen. However, if you have that kind of system, that's what Germany has done. They're prepared to offer to those who supply solar electricity the equivalent to the highest premium electricity. So to some extent, there is an incentive for them to install these things and sell. In India, today, presently available solar photovoltaic systems generally end up with a generation cost of 18 to 20 rupees per kilowatt hour. Compare that with about 2 rupees to 250 for coal-based power in, let's say, areas remote from coal mines. And in coal mine area, it may be even only about 150, 1 rupee 50 paisa. Nuclear, I've done, because I was chairman of the tariff of the nuclear power stations report I made last year. We have compared all our nuclear power stations hitherto built. The range is between 1 rupee to 2 rupees 80 paisa. For the future, we are pegging a number of 350 to 4 rupees for power plants to be built 5, 6, 7 years from now. Now, solar has to really come down a great deal, and that can happen in two ways. We require a new technology. See, right now, the photovoltaics have a very, very low efficiency, only about 12%. So much of the incident energy you're not utilizing. This is because the photovoltaic device is selective. It's only picking up some particular wavelength of the sun's energy. If you want to do much better, you've got to use what are called as multiple layers, thin film technology, a whole lot of special materials, each of which is capable of absorbing some specific bandwidths of the solar radiation. You can do that in theory, and in practice people have demonstrated 40–50% efficiency, but they're extremely expensive cells to make. Now the big challenge is how to bring the cost down there. Second thing is mass produce and so on. But it's going to take a long time before really costs come to a point where they can be accepted as economic. There will be subsidies provided for some period of time in order to encourage, is part of policy, the so-called action plan on climate change, which Prime Minister Manmohan Singh announced, I think, a year or a little bit more ago, envisages a fair amount of push for solar. But really what has not happened in India, I mean, of course, I do not know if there's any physical scientists from Indian Institute of Science here. Even our best scientific institutions are doing not a great deal of work on solar energy technologies. Of course, Dr. Amurthy is here. I think he may well correct me. We all want this to happen. And now, for instance, the only people who made good solar quality, good quality solar photovoltaic cells is atomic energy. We made it for space applications. So now we've got to ask our own people, because they've got good metallurgists, good material scientists and all that, but do something. Everybody else is talking, and our industry is hardly doing anything. All that they are doing is they're putting together something that they imported here and there, they're marketing. Well, one thing that's good that's happened is we are having, at least in Bangalore and other places, water heaters, because it is a crime to use high quality energy, electricity to heat the water. At least that has changed as a result of some push that we have got on shall we say, reduction of electricity, or some rebate given to you if you use hot water heaters and such, like solar heaters and so on. But all of this must happen in a big way. But I do say that for a country which claims, quote unquote, that we have the third largest S&T manpower, the contribution that we have done in India on solar energy technology is really not at all terribly impressive. So much must be done. So all of us say this, but we've got to somehow make this happen. So for quite a long time to come, solar may not really provide much of an answer. We've done some long-term studies on energy. By 2050, electricity supply, we think, this may be wrong, but we think that we require roughly 40% coal-based with clean coal technology, 40% nuclear, best possible nuclear technology, and 20% renewables. That would include solar, wind, and so on. Yeah. Why don't you just use the microphone?
Today there was a report, in Japan, the Daiichi plant, they were using nitrogen. I didn't, follow why they are using nitrogen to, press the. It was against radiation or for some other purpose?
To prevent further heating, to further oxidation of the fuel, to see that, even the original design, of course, I didn't point out, in one of those slides, it's called inerting. You see this so-called Drywell, the original intent is to put nitrogen, that is, you fill up with nitrogen and not air, so that even if you have a hydrogen release as a result of the fact that some part of the uranium fuel is exposed, and you have hydrogen is produced by this zirconium water reaction, that doesn't explode. So the idea is that the Drywell is filled up with nitrogen. If they are doing nitrogen blanketing, it is see that they prevent further oxidation of the fuel. Well, if it oxidizes, it will spread aerosols and so forth. So that's one of the ways to mitigate. Because hydrogen are gone, you remove the oxygen, so you remove the oxidation potential.
Well, I informally announced to see that I had to regret to see that once this was scheduled and it was cancelled because of the intervention of the cricket match. It's not my own or NIA's doing. But so many requests came on that afternoon that they didn't want to miss either of these two talks, but at the same time they were not prepared to miss the cricket match also. So we have to adjust these things, and we apologize for dislocating the original project program. and also inconveniencing both the speakers to see if we enjoyed the two exposition immensely, and we are grateful to Dr. Rajendran and Dr. Srinivasan. Thank you very much. Good night. Good night.